You probably already saw some advanced engineering articles, or maybe even textbooks, where the authors use some weird symbols to write their formulas. And you wondered, like, how in the world I could understand any of it, if I even don't know what those symbols mean, and I have no idea where to search for those definitions. I want to make your life easier and to tell you that most probably those symbols were borrowed from the theory of sets, or mathematical logic. In this lecture, I will show you some of those symbols. Now, since we are talking about notation, you will need to stop frequently, to reflect on the material and to take notes. If you're just watching this video without taking notes, you're just wasting your time. We will start with explanations on sets. A set is a collection of different objects, and this is not formal definition because there is no formal definition in math for sets, but intuitively we understand what it means, collection of different objects. Those objects which are part of that set are called also elements of a set. If you want to write some set as list of numbers or list of some objects, you write it in curly brackets like that. For example, set A equals bunch of numbers like 2, 5, 3, 7, 123. This set consists of 5 elements, which are basically numbers. We can define set B as all of the numbers which are greater than 5. Clearly this set is infinite because you have infinite number of numbers which satisfy x larger than 5. Set C is defined as 3 different names of the colors which are red, green and blue. So this is a set of 3 elements, colors. Subset includes elements of a given set. So if you have some set A, any part of that set is called subset. For example, numbers 3 and 7 will be a subset of the entire set A. Usually sets are denoted with uppercase letters and elements with lowercase letters. We want to know when we can say that 2 sets are equal between them. But before that, we need to understand a few important properties of the sets. First of all, the order of elements in the set is not generally important. So you can change the order the way you want, it will not change the set itself. Also, if you list in the same element multiple times, it's not changing the set, so you can put multiple times the same element in the set. This is the same thing as you are putting it only once. So in terms of notation, you also need to know that vertical bar or colon mean such that. So we will see example of that in a second. The following sets are equal if and only if they have the same elements. And as I said, you need to remember that the order of elements is not important, and number of times that you put in the same element is also not important in that case. So let's see 3 examples here. Red, green, blue set, which is here, is exactly the same thing as green, blue, red, because I just changed the order of colors here. Now, the set 1, 2, 3, 3, 3, 3 is the same as x such that, so this is that symbol, that x equals to 1 or x equals to 3 or x equals to 2, which means it includes only elements 1, 3 and 2. And you can also write that this is the same set as 1, 2, 3. This is the same thing. Now, the set 1, 2, 3, 4 is clearly not equal to 1, 2, 3 because it includes additional number 4. So those sets are not equal. Okay, now we can learn more about new special symbols from theory of sets. And this is related to membership. We say that X belongs to A and using that symbol. And this means that A includes that element X, which means X is a member of A or belongs to A. Example, number 5 belongs to set of all X's between 0 and 10. So this sentence is basically true because 5 actually belongs to that set. It's between 0 and 10. Another one, 5 belongs to all X such that X larger than 10 is false because 5 is smaller than 10. This symbol means that the element X does not belong to set A. So it's not a member of set A. For example, 5 does not belong to that set which is X such that X larger than 10. As expected, of course, 5 is smaller than 10. Another symbol that we need to learn means that all elements of the set A are also in the set B. So basically, set A is a subset of set B. This is a symbol of subset. You can go also the other direction and to show that set B is subset of set A. It means that all elements of the set B are also in the set A. Sometimes we are not using that equal part, which means we're using just Z symbol or Z symbol. This means that they might not be equal, only included inside of the other set. So let's see some examples. Set 1, 2, 3 is a subset of 1, 2, 3, 4, 5, which is obvious. The subset red and green is a subset of the entire set of all possible colors, of course. The most basic operation on sets are union and intersection. The union of number of sets which is larger than 2 or equal to 2 contains all of the elements in all of the sets without repetitions, which means if you have one set and another set, their union is all of the elements of both of the sets without repetition. The union of sets A and B is the elements in either set, A or B or both. Symbolically, we write it like that. This is how you write union of two sets. For example, if you have set 1, 2, 3 and another set 3, 4, 5, their union will be all of the elements in both sets, which is 1, 2, 3, 4, and 5. Pay attention that element 3 you have in both sets, so you don't need to repeat it, because it will not change the final set. Now, the intersection of two or more sets contains all of the elements that are common to all sets, which means you're finding only common elements in both sets or more. So the intersection of sets A and B is joint elements of A and B. Symbolically, we write it that way. So this is a symbol of intersection of A and B. For example, the common element of 1, 2, 3 and 3, 4, 5 is that element 3. So this will be the set of single element number 3. Another useful operation with sets is complement. Technically, it means everything which is not in A. The complement of set A, and this is also denoted by small bar above the set, refers to elements which are not in A. For example, if A are all real numbers which are larger than 5, then complement of A in real numbers will be such real numbers which are smaller or equal to 5. So we started with those numbers, and somewhere here you have 5. You said that A set is all of the numbers which are larger. So this is set A. From this one to that direction, this will be the complement of A, all of the other numbers. The relative complement of A with respect to a set B, also termed the difference between sets A and B, written that way. This is how you denote difference between B and A. And this is all of the elements which are in B but not in the set A. Here are a few examples. Let's say your set B is 1, 2, 3, 4, 5. And then your set A is 2, 3. So you are looking for something which is in B and not here, which are elements 1, 4, and 5. Or another example, you have set of all real numbers and you want to remove all of the rational numbers. What is left is irrational numbers. One important property of complement that if you're taking set and then making complement one time, and then repeating complement, you get back to the original set A. So twice complement is the original set A. Venn diagrams are very convenient to represent sets in geometric way, in graphical or visual way. Basically, every set will be represented by some area, and this area could be overlapped with other areas, or intersect with other areas, or united with other areas. So we will try to describe those operations that you have here using very simple tools of union, intersection, or complement. Let's start with the first one. So we want A union with B. So this is A, this is B. You want basically all of the elements which belong both to A and to B. So let's draw that boundary. So all of the elements of A are inside of that brown thing, and all of the elements of B are inside of that blue thing. So technically we need to include both of them to make a union. So union of A and B will be something like that. This is union of A and B. Now we want to get union of A, B, and C. So we need also to include all of the elements that you have here, and the overall thing will be here. Intersection of A and B is basically all of the area which is common to B and A, which is that area. Next, we want intersection of A and B united with C. This is what we want to get. Now, A intersection with B we've got just a second ago, and now we need to add to that also all of the area of C, which means the overall thing will look like that. This will be A intersection B union C. Now, the last one is a little bit tricky. We want complement of A union with B. So, technically, we need to have all of the elements which are in complement of A and also all of the elements of B. So definitely all of those elements will be inside of that area, because this is B. So it should include all of the B. Also, it should include all of the not A, which means all of that. In other words, this will be the boundary. But the set we are talking about is not inside of that boundary, but outside. So this is a complement union with B. Now we can define a few standard sets, which are very popular. First of all, empty set. The notation says that you need to cross 0 like that, and this will be a symbol for no elements in the set at all. Sometimes you also can draw it as two curly brackets with no elements inside. For example, intersection of 1, 2, 3 set with 4, 5, 6 sets, which have clearly no common elements, is just empty set like that. Another very popular set is natural numbers. We talked about that before, but the symbol for that is Zn with double line here. Now, this set is defined as all of the numbers from 0 and counting up 1, 2, 3, 4 and so on. Now, sometimes in some references people are not including 0 in that set, so they start with 1. But this is not really important in most cases. Now, if you define some variable as x belongs to n, this means that just n is integer, that x is integer. And it's natural number, which means only positive integer. Now, integer numbers or whole numbers, which could be positive or negative, have their own symbol z. So this is x such that x equals 0, plus minus 1, plus minus 2, plus minus 3, and so on. So all of the whole numbers are integers, and the set of whole numbers is called z. The set of rational numbers is called q, and this is just ratio of two integer numbers. Now, pay attention that this is such a ratio xy that x belongs to z, so x could be 0, plus minus 1, plus minus 2, and so on, and y could be z minus 0, which means z which is not including 0 because you cannot divide by y equals 0. So we need to exclude 0 from that set. And then it will be rational numbers. It's just some sort of fraction. More general set of real numbers has r for the real part. This is the symbol that we are using. For complex numbers, we are using symbol c. And there is something which is called universal set, which generally we can use omega for that, or sometimes people are using u for that. Universal set is basically all of the elements we could think about for a specific problem. It could be like all of the numbers, or it could be all of the students, or it could be all of the colors, and so on. This is given to find complement to the set. So not always obvious what is complement of the set. It depends on how you define the entire possible options. So this set basically defines all of the possible options. And now we can get back to numbers and see dependencies between those numbers. So technically the simplest numbers are naturals, whole numbers, which are all numbers of integers including 0, but positive ones, are including of course naturals, integers which are z, including all of the whole numbers, and they include also negative numbers. Rational numbers, as we discussed before, include all of the integers. Real numbers include all of the rational numbers, and complex numbers include all of the possible real numbers. So each one of those sets make expansion of the previous set. It basically includes all of the previous set and makes more numbers of different kind. A mapping is just another cool word for function or transformation. If you have some function f of x, y, and so on, it has its own domain where the variables x, y, and so on are defined, and range, those are basically the values that f function is producing. So if you have, for example, some system of coordinates and you have some function, it might be defined in some specific range, and it has domain. So this is domain of that function. This is where this function is defined, and this is range, which is produced by that function f. Formally, the definition of function which maps from set A to set B is written like that. So this is function f, which is mapping from A domain to B range, and we will see a few examples of that thing. For example, you have f from R to R plus. This is a function which maps real numbers into real positive numbers. One simple example of that kind of function is just x squared. So we're starting with simple parabola, which looks like that. We're starting with domain, which is all of the real numbers, might be anywhere here, and the result will be only positive real numbers, like that. Another function, like that. So this function, from interval from -1 to 1, multiplied by interval 0, 1, which means you technically have 3 dimensions now. One interval, so let's say this one x, y, and f of x, y. So you will have interval on x, which will be from -1 to 1. Interval on y, which will be from 0 to 1. And we will have that kind of rectangle here. This is the domain of our function. And the result will be between 0, which is here, and 2 in terms of height. One simple example of that kind of function is, for example, x squared plus y squared. Clearly, if the inputs of x and input of y will be, x will be between -1 and 1, and y will be between 0 and 1, their sum clearly has to be between 0 and 2. So this is how you formally define that function. Another type of function, which is 3 variables and 2-dimensional as the output. So you have 2 elements in the output of that function. So it's multivariable function. This function is from r cubed, which is basically r multiplied by r multiplied by r. And it gets to r squared, which is r multiplied by r. So each element here will be from real numbers. R is real numbers. And each element here will be from real numbers. So you'll have 2 elements here and 3 elements here. Now I will show you a few additional things from mathematical logic that we could use, and they are very useful for shortcuts in writing different mathematical formulas. This symbol means for all. So this is kind of flipped upside down A. This is flipped left right E, means there exists some element. Or crossed E is does not exist. Those 3 dots mean therefore. 3 lines mean identical to. Arrow is then or implies something. This symbol means if and only if, and black square means the end of the proof. Sometimes you might also see one of those symbols, but they are less popular. Mostly mathematicians use them. So this is symbol for not. Sometimes you see something like that, not A. This is similar to complement, so generally in engineering we are using something like that instead. Or symbol, which is similar to union, or sometimes in programming we're also using that kind of symbol to say logic or. And that symbol is logic and, which is similar to intersection, or in programming many times we are using ampersand to say logic and between 2 sets. Now I want to show you a few examples to see how formally you could define existence of subsets or equality of sets and so on. I will follow those things from left to right and try to explain each symbol separately and to show you how you actually read that mathematical notation. So here it says that A is a subset of B if and only if for all x the following is true. If x belongs to A, which means that set A, which you hope to prove that this is subset, then it follows that that element x also belongs to set B. That expression technically means that if x belongs to A, then the same x belongs also to B, which means all of the elements of A belong to B. So this is how you formally write that thing. Another one where you don't have equality, which means that at least one of the elements of B is not in A. So how you write that formally? So A is subset of B which has some element which is, so element of B which is not in A, if and only if for all elements X, if X belongs to A, X also belongs to B. So this is exactly how it was in the previous one. Then you have and there exists such X that if X belongs to B, it will not belong to A. So this is what this expression says. There is such X, there exists such X, which belongs to B, but not to A. Now, the last one, you say set A equals to set B, if and only if A is a subset of B, and, which you can replace with ampersand if you like, B also belongs to A, which means B is a subset of A. So A equals to B if and only if A is subset of B is subset of A. This is what this expression means. So this is just for simple practice of all of those symbolics together.